Good morning, everyone, and thank you for joining our session today. I'm happy to be here to tell you about FRA's Train Occupant Protection Program, and specifically about a full-scale train-to-train collision test that we performed last summer at the Transportation Technology Center in Pueblo, Colorado. But first, I'd like to tell you a little bit about our research program. By way of definition, crashworthiness is the ability of a vehicle structure to provide sufficient space for the occupants to ride out a collision and of the vehicle interior to limit to survivable levels the forces and decelerations imparted to the occupants. The Train Occupant Protection Program comprises research on structural crashworthiness and interior safety of locomotives and intercity and commuter rail cars. The research focus is to improve the survivability of rail passengers and crew in accidents. Today I'll speak specifically about locomotive override prevention and our investigation of off-the-shelf options for securing wheeled mobility devices on trains. Inhibiting override or underride is of concern to FRA. Locomotives are susceptible to override in train-to-train collisions due to their relatively stiff underframe structure compared to other rail equipment. Conventional anti-climbing structures can deform on impact and lose their vertical load carrying capacity due to fracture as they crush longitudinally. This can lead to ramp formation and increase the likelihood of override. The photo on the left is an example of underride, in which the locomotive struck a standing train consisting of maintenance of way machinery at 23 miles per hour. The locomotive cab is crushed by the overriding freight equipment and the occupants were fatally injured. The photo on the right is an example of override, where an Amtrak locomotive struck a standing freight train at 33 miles per hour. The yellow jagged line shows the shape of the underframe of the Amtrak locomotive, which deformed considerably, highlighting the forces generated in such collisions. The purpose of our test was to demonstrate the effectiveness of two retrofittable crash energy management components on the front end of a passenger locomotive. The components consist of a pushback coupler, which telescopes on impact to bring the vehicle ends together, reducing the potential for lateral buckling or override. The telescoping action is triggered at a load of approximately 675,000 pounds. The deformable anti-climber is a bolt-on feature with crushable tubes arranged at different heights to accommodate interaction with most types of rail equipment. The upper tubes are positioned to align with the underframe of locomotives, while the lower tubes engage lower floor passenger cars. In a collision, the tubes collapse and engage the equipment at the colliding interface vertically to inhibit ramp formation, leading to over or underride. These photos show the results of testing and computer analysis of the individual components to confirm that performance met the specifications. The components were then installed on a locomotive and tested in two single vehicle-to-vehicle tests to further validate performance. The upper left image shows the pushback coupler after impact, in which the pushback action forces a larger tube into a smaller one. Expanding the tube absorbs collision energy and causes the paint to strip off. The upper right shows an overhead view of the deformable anti-climber. The top image is the collapsed test article, and the bottom is the computer simulation of the component test showing excellent agreement. The lower two figures show the sliding lug and the shear bolts. Once the pushback coupler has been engaged and exhausts its stroke, the sliding lug is loaded until the shear bolts fail and the assembly slides backward under the locomotive. This is a drone's eye view of the test, where we evaluate the performance of the pushback coupler and deformable anti-climber under realistic collision conditions. The moving locomotive with the CEM components and two passenger cars containing the occupant experiments is shown here. The impacting train has been pushed up to speed and released at a location which will result in the desired speed at the impact location and approach from the left. The release point is slightly uphill and the train is traveling with no persons aboard. The standing train is a similar locomotive connected to two freight cars. After impact, you can see that the two trains remain aligned, there is no indication of override, and the moving consists come to rest several hundred feet from the impact point. This is a close-up view of the impact from a camera mounted on the ground. It's difficult to see, but this shows the couplers engaging, pushing back, and the translation of the sliding lug after the shear bolts have failed. Again, no evidence of override or impending derailment. These are views of the deformable anti-climber after the train-to-train test on the left and after the locomotive to passenger vehicle test on the right. This shows how the different sets of deformable tubes are engaged, the upper or lower, depending on the type of equipment involved in the collision. Currently, there are no requirements for users of wheeled mobility devices to be restrained while riding in passenger rail cars. Effective securement or compartmentalization of wheeled mobility devices and the passengers seated in them can improve collision safety. 3 experiments conducted on board the train-to-train test using instrumented anthropomorphic test devices, ATDs or crash test dummies, manual wheelchairs, and containment systems used on transit buses. The test objective is to evaluate the feasibility of using these transit bus restraint devices on trains and the protection they may provide, just a proof of concept. Since passengers travel at the same speed as the train, in a collision, passengers continue to travel at speed while the train decelerates. The speed at which a passenger strikes some interior feature is the secondary impact velocity. The larger the travel distance, the greater the secondary impact velocity. Providing increased maneuvering space for wheeled mobility devices generally increases the impact velocity and the severity of secondary impact injuries during an accident. Therefore, it's recommended that passengers in wheelchairs are seated rear-facing with the wheelchair placed against a bulkhead wall or some other stiff structure to improve safety while maintaining passenger independence. ATD experiments on board the locomotive train-to-train test evaluated off-the-shelf restraint devices used in transit buses. The 3 experiments were arranged as shown here. The first is the quantum backboard only with an unrestrained rear-facing ATD. The second is the quantum system with a restrained rear-facing ATD, and the third is the Q-strain 1 system with a restrained forward-facing ATD. This is how the experiments looked before the test. The backboard-only option provides the most independence for the wheelchair occupant. No assistance is required to use this option. The ATD is seated in a commercial, off-the-shelf wheelchair. The second experiment is similar to the first in that it uses the same backboard. However, rotating bars at the base of the backboard grasp the rear wheels of the wheelchair, and the ATD is restrained with a 3-point seatbelt attached to the chair and the car body. The third experiment is similar to the second, except that here the chair is attached to the floor using J-hooks and straps. The ATD is also restrained with a 3-point harness. Experiments 2 and 3 use what we call surrogate wheelchairs designed for testing, since the purpose of our test was not to evaluate the structural integrity of the chairs themselves. Also, options 2 and 3 will likely require assistance from a crew member. This slide shows the response of the ATDs to the collision deceleration. The train is traveling to the right. The high-resolution slow-motion videos allow us to infer occupant motions during the collision. As you can see, there is substantial vertical motion of the ATDs due to the passenger cars bouncing on their suspensions. However, all of the devices remained attached and the ATDs remained compartmentalized, meaning there was no excursion from their initial positions. The test results can be summarized as follows. The pushback coupler deformable anti-climber integrated system performed as intended. All the CEM components activated and absorbed collision energy as designed. The shear bolts failed, and there was no evidence of vehicle-to-vehicle override. The ATD experiments were similarly successful. Wheeled mobility devices remained constrained throughout the collision event, and all the human injury criteria were met. The table on the right shows the applicable human injury criteria. Based on the sensors in the ATDs, we derived the injury metrics, all of which were well below the allowable limits. The next steps for this project include a deep dive into the enormous amount of data that we collected during the test, and using the data to refine our computer models so we can investigate different collision scenarios that we were not able to test. We're also looking to perform dynamic sled testing to investigate the performance of the restraint systems under different collision scenarios, or different crash pulses, different speeds, while we investigate innovative restraint solutions which provide safety while maintaining wheelchair passenger independence. Selected publications on this and related work are provided in this table, or with direct links to the documents if you have this document, or on FRA's e-library, whose website is at the top of the page. And finally, here's my contact information should you wish to learn more about this or other FRA research. Thank you very much for your attention today.